Hello. We'll look now at artifacts that affect the depth at which echoes are displayed. First, we'll look at the propagation speed artifact. The machine calculates the depth at which it displays each echo from the arrival time of that echo, assuming the propagation speed in all tissues is 1540 meters per second. If the ultrasound passes through a region with a significantly different propagation speed, then the depth will be displayed incorrectly. Let's look at an example. I'm showing here a liver with a fatty region somewhere in the center of it. Fat has a significantly lower propagation speed, around 1450 meters per second. So when the transmitted pulse travels through the fatty region, it's basically slowed down. When the echoes are returning, they too will be slowed down as they pass through the fat. So the echoes that have passed through the fatty region will arrive later than the machine would expect, and therefore they are displayed deeper than their true depth. As the beam scans to build up a two-dimensional image, it will see the tissue interface at its correct depth, except for those parts of the image where the beam is passing through the fat. And so we might see an appearance rather like I've shown in the right-hand side of this diagram. So if this was the diaphragm, for example, it would be at its correct depth, except for a region where there appeared to be a bump. Now, if instead of a slower speed, the region within the liver had a higher propagation speed than 1540, the bump would be in the other direction. The ultrasound would be travelling more quickly than the machine assumes, and therefore it would arrive earlier than would be expected for the depth of the reflector, and the reflector would therefore be shown more superficially than its true location. This is not a very common artifact, but you will occasionally see it. Here's an example of propagation speed artifact. It's been caused by a series of small veins, which we are scanning in cross-sectional area. The blood in these veins has a slightly higher propagation speed than the tissues around them. For this reason, the tibial bone, which is highlighted with the arrows, appears to have a rippling effect. It's not a straight, flat interface, as it really should be. And the reason is because the ultrasound travelling through the veins travels a little bit more quickly because of the higher propagation speed in the veins. A particularly common artifact is reverberation. The term reverberation is used when talking about sound, for example, the acoustics of a concert hall, and it refers to the sound reflecting backwards and forwards between the walls and ceiling and floor of that hall. The same thing happens with ultrasound. If you have two or more parallel reflectors, and if they are essentially perpendicular to the beam, then the ultrasound will reflect backwards and forwards between them multiple times, creating a series of equally spaced echoes. So one of the reflectors may be the probe face, or we may be just talking about reflection between two or more tissues which are relatively parallel. Reverberation is particularly common in the abdominal wall, and it therefore can degrade the quality of abdominal images. Let's take a look at a video first, which shows how this works. So here we have an example where the ultrasound is reflecting between the probe face and a tissue interface multiple times. Each time an echo comes back to the face of the probe, another echo is registered by the probe and displayed in the image. You can see, of course, that since the ultrasound is following the same path repeatedly, these images of that tissue interface will be equally spaced. And so we'll see the tissue interface in its correct location and then repeated at equal spacings over and over again, running deeper and deeper into the tissues. The other thing which is less obvious is that as the ultrasound pulse is travelling backwards and forwards through the soft tissue between the probe face and this reflector, it's going to be scattering from the soft tissues. And so the soft tissues are also imaged repeatedly. So we'll have both the tissue interface and the soft tissue between the two reflectors repeated again and again in the image, although they'll gradually become fainter due to attenuation, of course. Here now is a pair of diagrams, again illustrating how reverberation happens. On the left, we have again the example of the ultrasound reflecting back and forth between probe face and a tissue interface. This is likely to happen if the probe face is not well coupled to the tissues, for example, if there's not enough gel. Now what we can see, as I said, is a series of images of that tissue at equal spacing, gradually fading as they travel deeper and deeper into the tissues. On the right, we have something very similar, but now the reverberation is occurring between two parallel tissues within the body. Once again, the ultrasound travels backwards and forwards repeatedly between those two tissues, and so again we get a series of equally spaced echoes. And again, the soft tissue between those two reflectors is going to be repeated as well. Now let's look at a couple of images. On the left, we have a classic appearance of reverberation. We're looking at a full bladder, and you can see there are a series of parallel echoes which are highlighted by the arrows. These echoes are caused by reverberation within that series of parallel tissue interfaces which we can see between the bladder and the probe. So we get a series of parallel lines decreasing in intensity. Now note that this is evident, it's clear to us what is happening and that it is reverberation because the artifact echoes are falling into an echo-free liquid-filled region. If instead this was occurring in the liver, it's very likely that the artifact echoes would be comparable in intensity to the true echoes coming from the liver. And so we would see in the image a mix of the artifact echoes and the real echoes coming from the liver, and we wouldn't necessarily be aware that this reverberation was happening. So, as with many other artifacts, it may be that you can only really see artifact echoes and understand what they are and where they're coming from when they fall into areas that should be echo-free. On the right-hand side, we have a very different appearance, again in a liquid-filled bladder, but now you can see that it appears to be just a mass of soft tissue within the liquid-filled area. So this has been caused by reverberation within all those abdominal layers, and the result is not one crisp, obvious set of parallel lines, but rather a mass of echoes without any clear structure, looking like soft tissue. So these are two different examples of reverberation artifact causing echoes to appear deeper than the true location of the echoes. This is another artifact closely related to reverberation, which is why we have it here. This artifact is known as ringdown, and it occurs generally when we have a mass of small gas bubbles. Now, of course, that's a common finding in the GI tract, in the stomach, etc., that we have small gas bubbles, usually within a liquid, and those gas bubbles are very good scatterers of ultrasound. So we have strong echoes coming back from these gas bubbles. In addition, it's quite common that the size of the bubbles in relation to the wavelength of the ultrasound happens to be suitable so that some of the bubbles will resonate. So they will be stimulated at their resonant frequency, which means that they scatter even more strongly. So the net result of this is that we get a mass of bright echoes caused by the ultrasound scattering between these gas bubbles. The important thing to understand, though, is that this process goes on, that the ultrasound scatters back and forth between the gas bubbles. So the scattered ultrasound from one gas bubble will strike another bubble and scatter from it. And we also have the extension of the echoes due to resonance. And so the net result is a band of bright echoes extending from wherever these bubbles may be located deep into the image, often all the way to the lower limits of the image itself. Let me show you two examples. On the left, we have ringdown caused by a relatively small mass of gas. And so you can see we have a bright line. As usual, this artifact is parallel to the beam direction, and it extends all the way to the bottom of the image. Notice that a characteristic of ringdown is that there's no real structure to that bright band of echoes. It doesn't look like normal speckle. It doesn't look like soft tissue. It has a completely different appearance, which immediately jumps out at us and tells us that's probably ringdown, and it's probably caused by gas bubbles. On the right, we have a much more spectacular example due to a large number of gas bubbles. And so now we can just see a mass of bright echoes, and you can see right away that this is going to completely prevent us from imaging the tissues within that region. So this is one of the major things about ringdown artifact and gas in general, that it can block us from imaging deeper than the location of the gas. In this case, if you needed to see those tissues, you'd have to find an alternative window, or you'd have to ask the patient to come back and prepare them in a way that minimized the presence of gas bubbles. Now, there are other possible causes of this same appearance. For example, needles and other metallic objects like guide wires can also resonate and cause an appearance very, very similar to this. So ringdown may have other causes at times, but generally, if there's no reason to think there is something like a wire present, then you can be pretty confident you're looking at gas bubbles. A little bit similar is this artifact known as the comet tail artifact, because you've basically got a bright echo and then a tail on it. And notice again, this tail is parallel to the beam direction. So this is similar to ringdown in that something is resonating, so the ultrasound is bouncing backwards and forwards in a crystalline object, and the difference between this and ringdown is that it's relatively short-lived. So this is like ringdown, but it's coming from discrete objects, which are generally crystalline objects, for example, cholesterol crystals, microcalcifications, etc. And it's short-lived because the energy is fairly rapidly dissipated due to the nature of the objects causing the artifact. So this very distinctive appearance tends to be a good indicator of the presence of some kind of crystalline material. And the last of our depth-related artifacts is range ambiguity. This occurs if the machine transmits while it is still receiving echoes from the previous transmit pulse. So if it does that, then there will be echoes from the previous pulse mixing with echoes from the new pulse, and the machine will be unable to correctly determine the depth the echoes are coming from. And so there's basically an ambiguity about whether the echoes have come from the new transmit pulse or the old transmit pulse. Let me show you a diagram. In the top half of this diagram, I'm showing the normal process that the machine tries to achieve. So it's transmitting, an echo comes from a relatively deep object, and then the machine allows enough time for all of the detectable echoes to fade away due to attenuation, and then it transmits again. So there's no uncertainty about the depth. this object will be shown at its correct depth, which will be calculated from the delay time t. In the bottom diagram, I'm showing what would happen if we doubled the PRF in some way, or if the machine doubled the PRF. And you can see that that echo is still occurring at that same time t after each transmit pulse. However, the machine is transmitting before that echo is received, and so when it receives that echo, it isn't able to determine whether that echo has come from the new transmit pulse or the previous transmit pulse. And so it displays it at two different depths. One of them calculated from the time t, so that's the correct depth, but then at a more shallow depth calculated from the time t dash. So basically the image of this, the object causing this echo, is going to be duplicated more superficially when we have range ambiguity. Again, this is a fairly unusual artifact. Let me show you an example. On the left, we have an image of a filled urinary bladder, and this is when the machine is operating normally. In this case, the sonographer was playing around with the focus controls and selected a setting of the focus controls that was very unusual. And this, for some reason, caused the machine to increase the PRF, the pulse repetition frequency, to the point where range ambiguity occurred. You'll see now that there's an echo through the middle of the bladder, and you'll see that I've marked a couple of points in the rear wall of the bladder with capital X and Y, and then this other set of echoes I've labelled with a lowercase x and y. The reason is that the echoes shown halfway up the image is a duplication of the rear wall of the bladder. And so the point labelled with a capital X has replicated to the point labelled with a lowercase x, and the same for the point y. Now, it's not an exact copy of the rear wall because of the shape of the scan. So it's the format of the curved probe means that the depth dimension of the artifact echoes is correct, but the width has been scaled to a smaller size because of the way the scan lines radiate when this image is formed. So the scan lines are not parallel, and therefore the artifact echo is a copy of the rear wall but scaled laterally because of the diverging scan lines. Now, all the sonographer had to do to make this artifact go away was to go back to a more normal setting of the focus, and it disappeared. So this was basically an aberration. It can, however, occur when you're scanning in an area with much lower attenuation than the machine is expecting. The machine has to estimate the penetration depth so that it knows when it will be okay for it to transmit again. If the attenuation is very low, then penetration can be much larger than expected, and therefore the machine can wrongly estimate the limit of penetration, and therefore range ambiguity can occur. In summary, we've looked at several artifacts that affect the depth at which the echoes are displayed. The first of these is the propagation speed artifact, which is not usually going to be particularly evident or important. Reverberation is a common artifact, and therefore it's important to understand it. Remember that reverberation is caused by ultrasound reflecting backwards and forwards between parallel tissues which are approximately perpendicular to the beam direction. One of the ways to minimize reverberation is to tilt the probe so the beam is no longer striking the tissues at perpendicular incidence. Reverberation is important because it does happen frequently within the abdominal wall and the various tissue layers within that wall, and it therefore causes a series of artifact echoes to be displayed deeper, for example in the liver, degrading the quality of the image. Ring-down artifact occurs mostly with gas bubbles, and it can be useful if gas bubbles occur in areas where you don't expect to find them. But most of the time it's a problem, or at the least something that doesn't help you. Comet tail artifact is potentially useful because it highlights the presence of some sort of crystalline material. And range ambiguity is something to be avoided because it gives a very misleading appearance, a doubling of tissue structures, and the machine normally manages to avoid range ambiguity, but occasionally it won't be successful in doing this.